To recap, we are looking at the idea of the nth roots of complex numbers. Our example was z cubed is equal to 1 with some algebra, and we were able, or what we could say indices laws, we were able to suggest that we could represent it as a straight line on the real axis with no value on the imaginary, because it is simply equal to 1. There is no imaginary number here, wherein z is x plus iy. So if z equals x plus iy, then x plus iy must equal 1. The y does not exist. There is no imaginary value. It is equivalent of 1 plus I, 0. This x plus iy system, however, holds us back in terms of our conversation on what it means to find the nth roots of a complex number. And that is to say, what we then did is we looked at this version r cos theta plus I sine theta using basic trigonometric rules to remove the x and y and put them in the form cos theta and sine theta, factorizing out the r. As a result, what we can then say is, in order to get a value of 1, remember this value of 1, if for x plus iy, it's easy to consider that therefore the y we would just say does not exist. There is no imaginary value of y, it does not lift up off the x-axis, and the x can just be 1. But when you put it in cos theta plus I sine theta form, the question becomes, what value of cos theta along the x is 1, and what value of sine theta along the y is 0? And that is to say, cos 0 is 1, and sine 0 would be 0. And so instead of stating, as we described in the past, x plus iy equals 1 or z equals 1 in this form, we are now able to look at it in terms of cos theta plus I sine theta, where theta is 0, equals 1. And I made a statement here simply saying it can be said that we can get the same value of y for a cosine or sine function when we do a full rotation at 2 pi around a conceptual circle, or 2 pi along an x-axis. So this value of cos 0 and sine 0 is only one of multiple outcomes that will produce the number 1. And this is well known in trigonometry, and if that's not something that you're comfortable with, I would suggest we go back and take a look at the identity, the concept of the sine and cosine function. But I'm going to go for it just a little bit here, just in case, or to remind us just a little bit as to what I'm talking about. But for now, what we can conclude is that this is a representation of this same line of 1, but in a trigonometric form as a complex number. So here we have a poorly drawn but gets to the point concept of a cos theta. And you can see that the value of cos theta that we wanted, which was 1 up here, so this at this point we can say is 1, is the same as it is here. So this is also equal to 1. And if I was to carry on, I'm going to very poorly draw this cos theta like so. If I was to carry on in something like that, bear with the diagram, that there will be another 1 value up here, and if I was to carry on to the left, there will be another 1 to the left side, as just trying to describe there. That is to say that this value of 1 will repeat on a cyclical basis for the cos function as it goes round and up back to that point. Both functions, cosine and sine, need to share the same theta, such that the real axis associated with cosine is 1 and the imaginary axis associated with sine is 0. So we cannot pick any values of theta that cause repetition or cycles. We have to pick the value of theta that will mean that cos will give you an output value of 1 and sine will give you an output value of 0. But note that both these functions cycle. So for example, at this point here, we've got our value of 0 as I've depicted in this diagram. There is our value of 0 there, but there is another value of 0, and again it will cycle as the sine function continues on its pattern to produce values of 0. And these are at the same, although this is not placed correctly, that is the same position on the axes, so they both share the same values of theta for us deciding that we needed a 1 for cos theta and a 0 for sine, a 1 for cos theta, 0 for sine, and so on and so forth. So what I suggest in this last part here is simply, this is true not just for one value of theta, but for infinitely many multiples of 2 theta in both the positive and negative direction. As I described, you can go this way and find large numbers or infinite situations in which the x-axis you can pick an x-axis value that will produce a cos value of 1, and infinitely many ways both the x and y direction. That is to say, I can go in both the x direction and I can go in the y direction as well in order to find output values of 0 and 1 for both cos and sine. And we need to recognize this going forward.